We're absolutely swimming in an ocean of data. It's everywhere. The stock market, weather patterns, our own social media feeds, and as humans, we have this deep, fundamental need to find the patterns hidden inside all that chaos, to find the signal in the noise.
So that's really the big question, isn't it? How do we take all this raw information and turn it into something genuinely useful, something like insight, or understanding, or even the power to predict what's going to happen next? All right, let's get into it.
Well, probably the most powerful tool we have for this quest is something called a regression model. Now, I know that might sound a little intimidating, but the core idea is actually incredibly simple. It's really all about trying to draw the best possible line right through a cloud of data points. That's it.
To put it a bit more formally, a regression model is just our mathematical way of trying to pin down the relationships between different things. It's a fancy way of asking, hey, if I know about this variable, what can I confidently say about that one?
And pretty much every one of these models has three key parts. First up, you have the response. That's the main thing, the one variable you're trying to understand or predict. Then you've got the regressors. Think of these as all the other variables you're using as clues to help explain that response. And finally, and this part is absolutely crucial, you have the error term. This is basically the model's dose of humility. It's our way of admitting, look, this model's never going to be perfect. There's always going to be some randomness, some stuff we just don't know about.
So, okay, we've got our data, and we want to draw a line through it. Simple enough. But which line? I mean, there are literally infinite possible lines you could draw. How on earth do we pick the single best one, the one that actually represents the true pattern?
Well, as it turns out, there isn't just one simple answer. In fact, there are two major and kind of competing philosophies on how to find that best line. And they come at the problem from completely different angles.
On one side, you've got the method of least squares. This is the ultimate pragmatic approach. It basically says, forget all the philosophy, just find the one line that makes the total gap, the error between the line and all the real data points as tiny as possible. Simple. But then, on the other side, you've got the Bayesian approach. This one is way more philosophical. It says, let's start with a prior belief about where the line probably is. Then we'll treat the data as new evidence to update that belief into a smarter, more informed theory, which we call the posterior.
And this is the whole Bayesian idea in a nutshell. Your new belief, the posterior, is a product of the evidence from the data, that's the likelihood, and your old belief, the prior. It's really just a beautiful mathematical way of describing how we learn from experience.
So we have these two totally different ways of thinking, right? The pure pragmatist versus the learning philosopher. You'd think they'd give you different answers. Well, this is where the story takes a really surprising twist. I mean, really think about that. One method couldn't care less about anything but the data in front of it. The other is all about evolving a belief system. You couldn't come up with two more different ways to approach the problem. And yet, they often land on the exact same mathematical answer, which is kind of mind-blowing. How is that even possible? How can two completely different paths lead to the very same destination? Well, the answer lies in one single, powerful concept. That secret ingredient is something called regularization. Put simply, regularization just means we add a penalty to our model if it gets too complex. We're essentially telling the model, look, I don't just want you to fit the data points. I want you to find a simple, elegant pattern. And I'm going to penalize you for getting too wiggly and complicated.
Now, the whole reason we do this is to avoid a massive problem called overfitting. That's where the model doesn't learn the real pattern at all, it just memorizes the random noise in the specific data it was trained on. So regularization makes our model more stable, more likely to work on new data it hasn't seen before. But, and there's always a but, this stability doesn't come for free. And that little but brings us to the fundamental trade-off that every single person who builds a model has to struggle with. It's a classic push and pull, and it's known as the bias-variance dilemma.
This quote from the source material just hits the nail on the head. It says that when we add that regularization to make our model more stable, our final answer becomes biased. Okay, so in plain English, what does that mean? It means the very act of making our model more stable and less jumpy introduces a totally different kind of error. We're basically trading one problem for another.
Let's break that down. Bias is all about accuracy. A low bias model is really flexible. It can capture the true pattern really well. But it's also at risk of capturing all the random noise and overfitting. Now, variance is all about consistency. A low variance model is stable. It gives similar answers even with different sets of data. But the risk there is that it might be too simple and miss the real pattern completely.
The key takeaway? You can't have it all. If you push down variance, your bias tends to go up, and vice versa.
You know, this is a pretty abstract concept, so how can we get a better grip on it? Well, the best way I've ever seen is with a simple analogy. Just think about target practice.
Okay, so imagine the bullseye on a target is the truth, the real pattern we're trying to hit. Bias is how far, on average, your whole cluster of shots is from the center. So a high bias model is like consistently missing the target in the same upper left spot. Variance, on the other hand, is how spread out your shots are from each other. A high variance model is like taking shots that are all over the target. So what do we want? Well, obviously we want a tight grouping, right in the center, low bias, and low variance. But in the real world, with limited data, that's almost impossible to get.
So if we're forced into this trade-off, how do we decide what to do? How do we navigate this dilemma? Well, believe it or not, we can find some really solid guidance from a philosophical principle that's been around for centuries.
And that guiding idea is called Occam's razor. It's the simple but profound idea that when you're faced with a bunch of different explanations that all seem to fit the facts, you should choose the simplest one. And modeling this means if you have two different models that both seem to explain your data pretty well, you should always prefer the less complex one.
Now, this ancient wisdom actually has a modern statistical name. It's called the Minimum Description Length Principle, or MDL, and it reframes this whole quest in a really powerful way. It says that finding a pattern is actually the same thing as finding a way to compress information. The best theory is the one that gives you the shortest, most elegant description of the data. It's this incredible link between understanding something and being able to explain it simply.
And that leaves us with one last fascinating question to think about. In our quest to find the signal in the noise, to draw that single best line through our data, we're constantly trying to balance this tension between accuracy and simplicity. And it really forces you to wonder, when we build these models to make sense of our incredibly complex world, is the simplest story really always the truest one? Or does the real truth sometimes hide in the complexity we chose to trim away?